So yesterday we got as far as talking about the movement of gas in and out of the alveolar space. We spent a lot of time talking about the conducting zone and the respiratory zone, talking about the epithelial and smooth muscle effects of changing the diameter of those delivery tubes. And we ended up with a discussion of compliance versus elastic recoil. And I've just put this up here to formalize this. I'll never ask you this equation. Some of you like numbers. And this is the formal description of compliance. Compliance is defined as the delta phi, the change in volume divided by the change in pressure. We could equally have talked about this in terms of elastic recoil. But elastic recoil is the inverse, so that would be delta P divided by delta V. And of course, this is dV over dP if you're using calculus. So I'll tell you really quickly at the beginning of the lecture a way of thinking about this in everyday life. But most of today's lecture is going to talk about the gas exchange itself. We talked last time about bringing the oxygen down into the alveolar space. We talked about oxygen diffusing from the alveolar space, from the air in the alveolar space, and into the blood and therefore into the erythrocytes. But what we want to do today is see exactly how that gets done. And to talk about this in some sort of quantitative way, we have to begin with something called Dalton's law of partial pressures. It's a very simple idea. Dalton's law of partial pressures simply says that the total pressure of a gas is the sum of the partial pressures of the gases in the mixture. Now, for the air around us, we're going to find that the gases in the mixture are oxygen and nitrogen. If you talk to a climate scientist, they'll tell you about argon and other trace molecules. But we're going to think about 21% oxygen and 79% nitrogen. That tells us that the total pressure of air is made up of 21% of the pressure by oxygen and 79% of the pressure by nitrogen. We can then formalize this by talking about atmospheric pressure. Now, atmospheric pressure is just a way of describing concentrations, and I want to emphasize that as we work through this, as we talk about these arcane numbers of millimeters of mercury, which are used hardly any place else except in biology and physiology, that these arcane numbers that we're going to talk about here are a reflection of concentrations. And I'll say it again, but it's no accident that Dalton is the guy in the early part of the 19th century who sorted out concepts of molarity and concentration. And it's no accident in this chemistry experiments sorting out molarity and concentration. He also developed this idea of partial pressures, which is just another term for concentration. And we're going to find that we can work our way through this. We can start with the idea of the atmospheric pressure at sea level. If you're standing on the beach in New Jersey or in Florida or in Portland, pretty much at sea level, then the air above you, the mass of air above you, all the way out into outer space, that mass of air will be able to raise a column of mercury 760 millimeters, 3/4 of a meter. But as you go up in altitude, there's less and less mass of air above you. So by the time we reach, if you put your phone away, I'd appreciate it. If we reach an altitude where we're sitting in this room of about a little over 5,000 feet, about 1,500 meters, at that point, the air above us can only force this column of mercury up about 630 millimeters. By the time we get to tree line of about 10 or 11,000 feet, we're down to 523 millimeters of mercury. And by the time we're standing on top of Mount Everest, the few people who do, we're down to 253 millimeters of mercury. All of this is simply saying that the higher we go in altitude, the lower the pressures. But wherever we go on the planet, in the atmosphere, these ratios are always the same. We always have 21% oxygen and 79% nitrogen. What changes, though, with altitude is the overall pressures. So we'll work our way through, then, the so-called partial pressures, the proportion of the atmospheric pressure that's generated by oxygen, the proportion of atmospheric pressure generated by nitrogen. And then what we'll do is we'll come down into the alveolar space, and we'll lay out the concentrations of gases down in the alveolar space. And as you walk through this simple table, you'll immediately recognize that these concentrations, in terms of percents, are a little different than in the air. That instead of 79%, we have 75% nitrogen. Instead of 21% oxygen, we're down closer to 14%. Because we're in an enclosed space, and we're going to see that all of these epithelial cells are covered with a layer of water, then that layer of water generates 100% relative humidity down in this space. So we find that 6.5% of the gas molecules in the alveolar space will be water molecules. We'll see here carbon dioxide is 5.2% of the molecules in the alveolar space. This looks like a small number, but in fact, if you compare that with the carbon dioxide concentrations in the air around us, the concentration of carbon dioxide in the air around us just passed 400 parts per million. That's 0.0004%. So the amount of carbon dioxide in the air around us is like 100 times lower than the amount of carbon dioxide in the alveolar space. This will have physiological effects when we start thinking about how we're going to use CO2 with its interaction with hemoglobin and how we're going to transport carbon dioxide as bicarbonate. But hold on to that idea until next week. The other concept that we have to walk our way through here when we lay out the concentrations of gases in the alveolar space is to remember that the epithelial cells are covered with an exquisitely thin layer of water, but nonetheless, there is a thin layer of water on those cells. That means for these gases, whichever of the gases, to enter the blood, those gases must first go into solution in that exquisitely thin layer of water. But going into solution now brings us to this concept of Henry's law. Henry's law simply says that gases go into solution in water in the proportion to their partial pressures. And I'll try to describe this in a real world terms and opening a can of beer to try to help you think through this. But fundamentally, all we're talking about here is that the higher the percentage of higher percentage of gas molecules, the more they're going to go into solution. It's just a direct proportion. Then finally, we'll finish with this discussion of an oxygen dissociation or association curve. What we're going to do is going to draw a very simple curve. We're going to plot the percent saturation of hemoglobin versus the partial pressure of oxygen. And we're going to find that once we get up into the neighborhood of about 100 millimeters of mercury, that the hemoglobin molecules, the iron in the hemoglobin molecules, is fully saturated. We're going to find that this is not a straight line curve, that it's a sigmoidal curve, that the shape of the curve, the sigmoidal nature of the curve, tells us there's something called cooperative binding. It tells us that the binding of the first oxygen molecule to hemoglobin is pretty low. But once we bind one, we improve the probability of the second, the third, and the fourth. This provides a sigmoid curve and tells us a little bit about how oxygen is coming onto the hemoglobin and also how it's being given up. When we draw this curve, then we'll also incorporate into this curve what happens when we're in the alveolar space, where the alveolar space has 106 millimeters of mercury, and what happens in the blood as that blood is returning in the pulmonary capillaries to become closely opposed to the alveolar space. The partial pressure of oxygen in the blood coming back from the tissues is in the neighborhood of 40 millimeters of mercury. We'll see when we draw this out that the 40 millimeters of mercury tells us that because of the sigmoid nature of the curve, that 3 of the 4 iron atoms in each of the hemoglobin molecules is still bound to oxygen. Because of the sigmoid nature of the curve, that means we're well up on the steep part of the curve so that it will be easy to put that 4th oxygen atom back onto the iron in the hemoglobin as it passes the alveolar space. But let me first write this on the board where we have compliance is equal to the change in volume divided by the change in pressure. Well, these are just symbols, and for me at least, I have a hard time getting my head around this, what it really means. And the best way I think I can illustrate this is imagining you're going to have a birthday party. And so you're going to go out and get a whole bunch of balloons. And so you go to the grocery store and you get these really, really cheap balloons. And you take those balloons that are in those plastic bags, you open up the plastic bag and you pull out one of those balloons, you give it a little stretch, and you put your mouth up to the balloon and you start to blow on it. And it's not particularly hard. You blow a little bit of air in, you have a delta P, and rapidly you get a change in volume. You have high compliance. These are compliant balloons. They're easy to blow up. Now, let's imagine you want to have some of those fancy balloon sculptures at your party. And so you go out and buy these special balloons that you can twist into all sorts of shapes and make into fanciful creatures. And you take one of those balloons and you try to blow it up. And you bring one of these balloons up to your mouth and you start to blow on it. And you increase the pressure, and you think you're going to have a stroke, and still there's no change in volume. These have very, very low compliance. They have high elastic recoil. And that's simply telling us that if you manage to blow them up and then you let the air out, they're going to collapse quickly because they have high elastic recoil, and this delta P will be rapid. The delta V will be rapid with respect to delta P. So basically that's just a formalization, and if you think about compliance, you think about elastic recoil, and you think about it with the lung, high compliance means it's really easy to breathe in. You have an easily expandable balloon. But if you have a fibrotic disease, where you've now begun to put more extracellular proteins around those alveoli, it's much harder to expand those alveoli, and you end up with alveoli much like those balloons we use for sculptures. We have very low compliance, high elastic recoil, and it's very difficult to get those to inflate. But let's begin here with the idea of gas exchange in the alveoli and Dalton's law of partial pressures. This was all worked out in the early part of the 19th century by this guy named Dalton. As I mentioned in the introduction, Dalton was important in the early days of chemistry by organizing the thoughts on molarity. So Dalton's law of partial pressures simply says that the total pressure of a gas is the sum of the partial pressures of the gases, of the gas components. Well, that's the formal definition. If you think about the air around us, the air that we live in all of the time, we find that air is 21% oxygen, and it's 79% nitrogen. Now, if you drill down into this, you have trace amounts of water vapor, you have trace amounts of argon, but by and large, air around us is 21% oxygen, 79% nitrogen. Now, over here, what I want to do is describe what we mean by millimeters of mercury. And again, I'll say this here, we hardly use this terminology of millimeters of mercury anymore in any other areas other than physiology and some biology. But the millimeters of mercury is defined as how high a pressure can raise a column of mercury. And in the old days, what they would do is they would set up a U-tube. This, of course, was a different kind of U-tube. And they would close the tube. They would fill this with mercury. And then at the top of the tube, they would generate a vacuum. So there's basically no air up here. So there's no air pressure. Down here, this end of the U-tube is opened atmosphere. So you can imagine there's air above this open tube. There's a mass of air above this open tube. There's a mass of air above this open tube that goes all the way into outer space. The mass of air at standard temperature and pressure at sea level, at a given temperature at the standard at sea level, can raise this column of mercury 760 millimeters. That's simply saying that we have a mass of air when we're standing on the beach in Seattle, and we have a column of air above us that has sufficient mass to force a column of mercury up 760 millimeters. As we go higher and higher in altitude, as we go to where we're sitting in this room, which was a little over 5,000 feet, a little more than 1,500 meters, by the time we get here, we have far less air above us than we had standing on the seashore. And so here in our environment, we can only raise a column of mercury to about 630 millimeters. If we were to go to Death Valley, where we're below sea level, then we'd have a greater column of air above us, and we'd raise the column of mercury a little bit higher. Simply saying that this measurement, the height of the column of mercury, reflects the total mass of air above us. And wherever we go on the planet, whether we're sitting in this room or whether we're standing by the Dead Sea below sea level, we always have the components of air being 21% oxygen and 79% nitrogen. If we're to take these numbers at sea level, it's 760 times 0.21, the percentage of the partial pressure being oxygen. So this is atmospheric pressure. This is partial pressure of oxygen. And this tells us that the partial pressure of oxygen here, the PO2, is now going to be 160 millimeters of mercury. Let me do it this way. This is proportion of air as O2. That means the partial pressure of oxygen, and we can formalize it, give it a number, is 0.21 times 760 is 160. If we do the same thing with 760 times 0.79, we come out to a number that's around 600. And I think you can see that as we go higher and higher in altitude, and this 0.21, the 21%, remains fixed, as we go higher and higher in altitude, and this number gets smaller and smaller, we're going to see that this PO2 level starts to go from 160 down to 140 to 130. I'll let you do the numbers, but simply if you take these numbers for here in Fort Collins, this number at 10,000 feet, and this number at the top of Mount Everest. If you walk your way through these numbers and multiply them times 0.21, you'll simply see that the PO2 gets less and less and less as we go up in altitude. Well, why is that important? Well, what we want to think about here is what's going on down in the alveolar space. We've made this drawing several times. And the alveolar sac is meant to be the opening here between these two parallel lines of alveolar epithelial cells. So this is meant to be an alveolar epithelial cell. And last time we drew this, and we said that right adjacent to the alveolar epithelium, right adjacent to the basilar surface of that alveolar epithelium, was a layer of endothelial cells. And then we said that within this pulmonary capillary, there would be these erythrocytes. And the erythrocytes are being driven through the pulmonary capillary by the contraction of the right ventricular myocardium. That's the force generating these erythrocytes through this capillary. And we're going to move them from left to right just by convention. I'm going to say we're going to move them from here to here. Meanwhile, you'll remember that over the tops, on the apical surfaces of all of these epithelial cells, is this exquisitely thin layer of water. We emphasized the importance of the water yesterday when we described how the surface tension of that water would contribute to the elastic recoil of the alveolus itself. Today, what I want to think about is the concept over here of Henry's law, which simply says, like Dalton's law, Henry's law says that gases go into solution in water in proportion to their partial pressure. The more gas you have, the more goes into solution. It's a simple linear relationship. Well, let me tell you a real-world story here that may help you hold on to Henry's law. So this is a can of beer. Could be a can of soda. And it has fluid in here. But we all know that if you shake one of these cans, it's not completely full of fluid. There's a little bit of what we call headspace. So there's an open area in here. Now, the gas that's in solution in this fluid is carbon dioxide. And if you look at the gas up here between the top level of the fluid and the top of the can, this basically is going to be 100% carbon dioxide. And since this is 100% carbon dioxide, and based on Henry's law, there's going to be an equilibrium so that carbon dioxide will leave and go back into solution. So it comes and it goes. But now we have as much carbon dioxide in the fluid as we possibly get in. Now we open the can. Now the percent of CO2 in atmosphere is 0.00004%. It's 400 parts per million. No, it's another zero. Is that right? Yeah. So 0.0004 CO2, 0.04%. So there's not much out there. The amount of CO2 in the atmosphere around us is not very much. Now we're worried about it. We're worried that we're inching this up by burning fossil fuels, or inching this up slowly from 350 to 400 and going up. And once we get up to around 450, we're generating such an insulating layer around the planet that we're going to have long-term effects on climate and the ability of the atmosphere to hold heat. But nonetheless, this is a really low concentration compared to the 100% that was at the top of the can. And you know full well what's going to happen if you leave this can of beer or soda open for any period of time. It's going to go flat. And the reason it goes flat, goes from 100% fully saturated to practically nothing, is Henry's law. And it simply says that Henry's law is telling us that the gases will go into solution in proportion to their partial pressure. When you get down to 0.04%, there's not much gas out there. And so the solution coming to equilibrium, you'll now come to 0.04% carbon dioxide in your beer, and that's flat. And so this is just an illustration of Henry's law. But all of these gases down here in the alveolus will now come to equilibrium with the fluid here in the blood vascular compartment in the pulmonary capillary. So let's look at some of these numbers because they're not the same as what we see in the air around us. When we talk about nitrogen, and of course, never memorize these numbers. I've got to read them off the board. Nitrogen is in the neighborhood of about 79.4%. No, 74.9. See, I got to read them. Oxygen is in the neighborhood of about 13.7%. The water vapor, H2O, is in the neighborhood of around 6.5%. And CO2 is in the neighborhood of about 5.2%. Well, if you change these numbers over to decimals, you have 0.137, 0.065, 0.052. And I'll let you go through the numbers of what millimeters of mercury this will be by multiplying, say, 0.052 times 760. This number, in fact, I'll give it to you. This is in the neighborhood of about 40 millimeters of mercury. When we go through this number for oxygen, we'll see this is in terms of about 106 millimeters of mercury. So those are the numbers we're working with. And again, we're using this arcane term of millimeters of mercury, but let me remind you that let's not think of millimeters of mercury, let's just think of relative concentrations. The Dalton's law and Henry's law says we can look at this as millimeters of mercury, but that's just telling us a kind of concentration. And if we look at the numbers and we imagine the PO2 in venous blood. Remember, we're asking here the partial pressure of oxygen in the blood that's returning from the systemic vasculature. Remember where this blood's been. It's been in the right ventricle, it's been in the right atrium, it's been in the vena cava. This is deoxygenated blood. If we measure the concentration of oxygen in the blood returning from the systemic vasculature and we express it as a partial pressure of oxygen, we get a number, the PO2, is in the neighborhood of around 40 millimeters of mercury. So now we can use these numbers as a kind of concentration. We can say that here in the alveolar space, 14% of the gas is oxygen. And that translates to 106 millimeters of mercury, whereas the concentration of oxygen coming back from the tissues, still bound to the hemoglobin, is down around 40 millimeters of mercury. That's just a fancy way of saying we have a concentration gradient. We have more than 2.5 times as much oxygen in the alveolar space as we have in the blood. As we've seen for concentration gradients of ions and any number of other things, ions in water, what have you, things move from a region of higher concentration to a region of lower concentration. So now we simply have generated a diffusion gradient. We have a gradient such that there's more oxygen here than here, and oxygen is going to diffuse down its concentration gradient and into the blood. The numbers for carbon dioxide here, the PCO2 for carbon dioxide, tells us we're in the neighborhood of 40 millimeters of mercury. If we take those same measurements down here in the venous blood, the blood returning from the systemic vasculature, down here we find the PCO2 levels are in the neighborhood of about 45 millimeters of mercury. again, thinking of these arcane terms of millimeters of mercury simply as concentrations, we can simply say there's more carbon dioxide here than there is here. So now we have a carbon dioxide gradient such that carbon dioxide is going to leave the blood vascular compartment and go into the alveolar space. We're just looking at this in terms of gradients. So any questions to there? Yeah?
Why doesn't nitrogen diffuse?
Why doesn't nitrogen diffuse? Nitrogen does diffuse. If we were to look at the partial pressures of the percent concentration, the percent of nitrogen here, it's going to be pretty close to 75%. And in fact, any of you who are divers will know this, because what's happening is you will have nitrogen dissolved in the plasma. Now, it's not binding to hemoglobin like oxygen. I mean, we carry a ton of oxygen here. About 70 times or 80 times more oxygen can be carried in blood because of hemoglobin than you'd expect just dissolved in the plasma. But we can still get nitrogen dissolved in this plasma. All right? So this is a worthwhile exercise to go through. So now you start diving. You go down 20, 30 meters. Now suddenly the pressures get to be greater. So these gases are going into solution in proportion to their partial pressures. So we've increased the pressure of nitrogen. So we put more nitrogen in solution in the blood plasma. Then we suddenly come up from 30 meters, and we come up fast. And we do the same thing there as you did when you opened the can of beer. You reduce the pressure, and now you cannot have as much nitrogen in solution in the fluid because the pressures are lower. And it comes out as bubbles, and that's nitrogen narcosis. You have all these little bubbles. You basically have fizzy blood because of the nitrogen coming out of solution, and that's because of the pressure change. And that's why when you dive, I think it's more than 10 meters, they want you to decompress at intervals all the way up. So what you do is you bring the concentration of nitrogen in the blood back to equilibrium with the concentration in the alveolar space so that you don't have this problem of the sudden decompression and the bubbling of the gases out of solution. Yeah?
So I don't remember if we went over this. What does the CO2 bind to in the blood?
What does the CO2 bind to in the blood? We did not go over that, but we will.
Okay.
We're going to find most of the CO2 is going to be transferred as bicarbonate. Okay. But we're also going to see that there's an effect of CO2 through its generation of carbonic acid. It's going to affect the hemoglobin. But let's come to that a little bit later. Yeah. So the question here is, when do we actually see the diffusion of oxygen across the epithelium? Is it when the alveoli are expanding, or is it when they're contracted? Pretty much it's all the time. The expansion and contraction through the elasticity of the alveolus that we talked about yesterday, all that's doing is allowing air to come in and air to go out. It's basically mixing the air. It's just a mechanical means of taking old air out and bringing new air in. If you spend a little time looking at birds, they do it differently. We have this bizarre situation where we lower the diaphragm, bring air in, and through those same tubes we take air out. Birds bring air into these sacs, these air sacs, and then they pass the air in one direction through the lung. And so they get a much more efficient exchange. And I don't want to get too deeply into that, but it's a really cool system. Yeah. So the question is this why we breathe out carbon dioxide? And it's a great question because, yes, we're breathing carbon dioxide from the blood into the alveolar space. And then as we breathe, as we ventilate, then we'll move that carbon dioxide to the outside space. But under normal circumstances, we retain a fairly high level of carbon dioxide down here in the alveolar space. Now, we'll come to this a little later, but if you breathe in and out really fast, and we've all done this as kids, and if you breathe in and out really fast and hyperventilate, you can lower this carbon dioxide level quite a lot. And that has effects on your willingness to breathe, because we'll see a little later, carbon dioxide in the blood is the signal to tell us to breathe. So if you breathe in and out and get this low enough, and get the blood concentration of CO2 low enough, you inhibit your tendency to breathe. Yes?
The next mechanics question, but like when you're training for like increased lung capacity for like cycling or diving or something, is that just increasing the mechanical capacity of the vessel, or is that more about?
So the question here is one of conditioning. And I find this really interesting. When you work out and you condition, you're trying to condition yourself for a long distance race, and you spend weeks or months doing this, you're not changing the ability to move oxygen into the hemoglobin. These will 100% saturate. Even when you have your rates up around 180 beats per minute, maybe at your age close to 200. When you have those high rates of heart rates and you're really propelling the blood through these blood vessels, the dwell time here is still in terms of a third of a second. That's adequate time to move enough oxygen onto the hemoglobin that all of the hemoglobin molecules are occupied. So this end is not where we condition. It appears where we condition is at the other end, at the muscle, and the ability of the muscle to extract the oxygen. Now, over time, I think there is a slight change in tidal volume. I think you get a little bit better at tidal volume, but mostly it's the ability at the far end, using the oxygen, where the efficiency is improved. It's not in the loading, it's in the unloading and the use. Yes, anything else? Okay. Then from there, let's now formalize this a little bit. Let's talk a little bit about the so-called oxygen dissociation curve. And I'll show this as a fairly crude drawing. And then I'll show it being accurately represented. But I want to give you a sense of what this curve means and how we can interpret it. So what we're going to plot here is we're going to plot percent saturation of hemoglobin versus the partial pressure of oxygen. And we're going to label this panel as the so-called oxygen association or dissociation curve. So this is the oxygen / hemoglobin association and its inverse dissociation curve. Now this curve is plotted so that on the axis we're looking at the partial pressure of oxygen, PO2. And what we're plotting on the ordinate is the percent saturation of oxygen, of hemoglobin rather. When we draw this curve, we find that the curve is sigmoidal. And the sigmoidal curve implies cooperative binding of oxygen to hemoglobin. So when we draw this curve, it looks a little like this. Where up here, we're at 100% saturated. So we're effectively 100% saturated here. If we follow this down from 100%, we see at this point we are at about 106 millimeters of mercury. No surprise that that's pretty much the partial pressure of oxygen in the alveolus. It's about 100 to 106 millimeters of mercury, and what that tells us is that at 106 millimeters of mercury, in the alveolus at 106 millimeters of mercury, as these erythrocytes are whirling by the alveolar space, we are occupying all 4 binding sites on every one of the hemoglobin molecules in those erythrocytes. But we'll also see that down here, at about 40 millimeters of mercury, we're still about 75% saturated. So notice what these numbers mean. At the partial pressure of oxygen in the alveolar space, in the lung, all of those hemoglobin molecules are occupied by, all the iron in the hemoglobin molecules are occupied with oxygen. But even when the blood is returning as deoxygenated blood from the systemic vasculature and the partial pressures are in the neighborhood of 40 millimeters of mercury, we still have 3 of the 4 iron molecules occupied with hemoglobin. Now, the next thing to think about is this odd sigmoid shape. First, we find the slope of the steep part of the curve is in the neighborhood of about 4. This is said to be a Hill coefficient. And the Hill coefficient tells us that there are 4 binding sites. Those 4 binding sites correspond to the 4 iron atoms in each of the hemoglobin molecules. But this sigmoidal shape tells us something else, too. It tells us that the binding of the number 1 carbon, the binding of the first carbon, is a fairly low probability event. Let me put this a little farther over. This is number 1. But the binding of the number 1 carbon increases the probability of the binding of number 2, which increases the probability of number 3, which increases the probability of number 4. This becomes important, particularly here between 3 and 4. And you'll notice that this number, where we have 3 of the 4 iron atoms occupied, is at 40 millimeters of mercury, is at the pressure, the partial pressure of oxygen in the blood is returning from the systemic vasculature. That means we're way up here in the steep part of the curve. And because of the cooperative nature of the binding of oxygen to the hemoglobin, it's fairly easy to bind that 4th site. If we were down here someplace in the curve, it'd be more difficult. But we can rapidly rebind the 4th site as those erythrocytes are moving by the alveolar space, because we're high on this oxygen association curve. We're in the steep part of the curve. The other point to make here, let's make it here, is that under normal circumstances, when we're at 106 millimeters of mercury, we're pretty much 100% saturated. Even if you look at the numbers here at altitude of about 630 millimeters of mercury of total overall pressure, we're still running about 95, 97% saturated. It's not until we get up above about 10,000 feet that we start to fall down in this curve appreciably. And once we start to fall down in this curve appreciably, that's no surprise, that's where the Air Force tells their pilots to put on an oxygen mask. They're a little uncomfortable with having pilots piloting $100 million airplanes when they don't have their hemoglobin fully saturated and delivering oxygen to their brains. So for caution, as soon as they get up about 10,000 feet, they want them to put on oxygen masks or be in a pressurized cabin. So any questions to there? What I want to do now is show you a pretty picture. And this is an accurate representation of what I sort of cavalierly put on the board. And I'll walk you through what each of these numbers means. But this is an accurate representation of the shape of the sigmoid curve. And the partial pressure of oxygen in the lungs is up here around 100 to 106. So we're fully saturated, 100%. We've got all of those iron atoms carrying an oxygen. And then when we look at the concentration of oxygen in the blood returning from the systemic vasculature, we're down here around 40 millimeters of mercury. And we follow this up, and we see that about 3/4 of the hemoglobin molecules are occupied with oxygen. And as we go to lower and lower partial pressures of oxygen, we come farther and farther down on this curve. When you look at this curve, what you want to think about is how tight the affinity, how easy it is for those oxygen molecules to hang on to the iron atoms. And so, for me, the easiest way to think about this is what's going to happen if we cool down the hemoglobin or if we warm the hemoglobin up. So you can imagine if you have these iron atoms clinging to an oxygen, and then you start shaking the hemoglobin more and more. So you start shaking the hemoglobin through increased energy. You heat it up. So now you have more energy here. If you have more energy and you're shaking the hemoglobin molecule more, you're more likely to shed that oxygen atom. But as you cool the hemoglobin down and it's vibrating less and less, then that oxygen atom is more likely to retain its hold on that hemoglobin molecule. And that's exactly what this next slide shows. And there's a certain amount of intuitive sense to this. So that, again, here we're plotting partial pressure of oxygen. Here we're plotting percent saturation. This is at normal, pretty much body temperature. Now imagine we warm things up to 43 degrees centigrade. We may not be able to get them that warm when you're exercising in muscle, but you can warm it up quite a bit. So now imagine you're exercising really hard. There's a lot of ATP being burned in the muscle. You're giving up a lot of heat. So you're warming the blood. If you have active muscle, you want to have as much oxygen available as possible to provide oxygen to the mitochondria. And so you can intuitively remember that out in the tissues where the hemoglobin molecules are vibrating, they're more likely to give up their oxygen. This greater likelihood to give up their oxygen is shown here in a rightward shift. So this tells you, if you go to a particular partial pressure, let's choose this one, you go to a partial pressure here, you're only about, less than 70% saturated, 43 degrees, but should be over 80% saturated at body temperature. Similarly, if you cool the blood, if you cool the hemoglobin, so that those iron atoms are not vibrating as rapidly, as you cool the blood, then they're going to hold on to those oxygen atoms more tightly. And so here we see a curve. We've moved the curve to the left. So when you move the curve to the left, that tells us there's a greater affinity of the oxygen for the hemoglobin. So we have this idea here, which is the temperature effect. And what I'm going to leave you with is imagine what's going to happen if we change the pH. Because when we change the pH, what we're going to see is the binding of the hydrogen ion to the hemoglobin molecule is going to give a rightward shift. And where are we going to have low pH? We're going to have low pH in those regions where we have high carbon dioxide concentrations. We've converted carbon dioxide into carbonic acid. We have hydrogen ion. We're going to get a rightward shift. We'll find on Monday that's the Bohr effect.